Hi everyone, my name is Schoebs and today I'm going to present our paper. The problem we're tackling here is a landmark localization, a supervised machine learning task similar to segmentation, where we train a model to pinpoint the coordinates of anatomical structures of interest. A particular challenge here we set out to address is capturing uncertainty in our predictions, since in reality the structure of interest typically spans more than the single pixel given by the label. Therefore, a model which can capture uncertainty by giving a distribution of likely locations is preferable. Typical approaches use deep learning, with CNN or transformers performing an image-to-image task, regressing a Gaussian heat map centered around the landmark of interest. However, the properties of this heat map are normally predefined before training, so cannot adapt to the landmark. Some approaches optimize the parameters of the Gaussian function, but this is over the entire dataset, not per sample. Further, the uncertainty given by this type of deep learning approach is not grounded mathematically and therefore not completely trustable. So an approach that can address these issues is Gaussian processes. These are probabilistic, non-parametric machine learning models. Interestingly, they can give us uncertainty in 2D in the form of a covariance matrix, which is exactly the same form we were trying to approximate with our heat map regression in the deep learning approaches. So specifically here we use a multitask convolutional Gaussian process using stochastic variational inference. So notoriously Gaussian processes are computationally expensive, and it was completely unfeasible to use a convolutional GP with the full or even downsized images. Therefore we use a two-stage approach. The first stage is your typical deep learning heat map regression, which gives us a coarse prediction of the landmark. Then we crop around this and pass it to the convolutional GP for a final mean and covariance prediction. So even so, this was still tricky to optimize, and we came up with some tricks such as setting our inducing patches around the stage 1 predictions, augmenting our training set by randomly cropping around those stage 1 predictions every epoch, and more. Overall, we managed to train our GP to achieve fairly good accuracy, achieving an average mean error of below 2 mm, shown by PE. This refers to point error, the distance between the mean prediction and the actual landmark coordinates. We chose to benchmark our results against a deep learning solution, which achieved greater accuracy overall. The subscript 2 and 5 in those CNN columns refer to the predefined standard deviation of the Gaussian heat map labels for our CNNs, which has a large effect on the accuracy. If we recall, the mean error only tells us part of the story, since in reality the landmark typically spans beyond the single pixel label. Therefore, we evaluate the quality of our covariance outputs using the negative log predictive density, or NLPD, where lower is better. Our GP approach gave impressively low NLPD measures, which is a good news since the mean estimate significantly affects the NLPD value. Therefore, if we can better optimize the training and improve the mean estimates of the GP, the uncertainty should be of a significantly higher quality than the deep learning based approaches. So here are some example model outputs. So for the CNNs, the size of the Gaussian is predefined and the model optimizes to reproduce it exactly. Therefore, it will be hard to interpret deviations from this as a trustable uncertainty. However, the GP outputs a covariance matrix directly related to its uncertainty over the input. We can see the GP's learned Gaussian blobs get bigger as we move down the rows, where the landmark gets harder. The CNN can even hallucinate multiple Gaussian blobs. Our approach is really just a preliminary exploration into using GPs for image regression tasks, a largely unexplored area in medical imaging research. Our work here shows that it's completely viable to apply them, and if we can work to address some of the optimization issues, there are some really interesting uncertainty estimation properties waiting. If you have any questions, ideas for improvements, or just interested in the project, please feel free to reach out to me or visit the GitHub with the code here. Thank you.